Welcome, ladies and gentlemen, to a force problems lecture. And what I'd like to do today is just solve some force problems so that we can get a little bit more practice with them, okay? So let's look at this first problem. Consider the Earth orbiting the Sun. If we approximate the Earth as orbiting in uniform circular motion, and this approximation is actually pretty good for Earth's orbit, it is almost circular. What is the acceleration on the Earth due to the Sun's gravity? How does this compare to little g, and what must be the strength of the force between the Earth and the Sun? And how does this compare to the strength of the force between you and the Earth? Alright, so let's look at this. We have the Sun, and we have the Earth, and we have some distance in between them, r, okay? And r equals 150 billion meters. And then it doesn't really give me anything else, right? So we're ultimately going to calculate the force. So I'll tell you that the Earth's mass is equal to 6 times 10 to the 24 kilograms. And then I'm not really sure what Earth's speed is, right? We know that the acceleration is going to be centripetal acceleration, so that's v squared over r. But I'm not really sure what v is. But I do know what t is. T is equal to 1 year, which is about 31.5 million seconds, okay? So I know that, and then I can think about it, and I know that t equals 2 pi r over v. So then v equals 2 pi r over t. And that means that centripetal acceleration equals 4 pi squared r. Sorry, this r I wrote in general, but for our problem I wrote it little r. Over t squared. So we can see in the units, this is really straightforward. We have meters on the top and we have squared seconds on the bottom. That's an acceleration, so that's good. And then sanity. Let's just point out that the acceleration is bigger as the period is smaller. Okay? So I would need a bigger acceleration to turn me if I was going faster around the Sun. And that makes sense. So that's good too. So what is this acceleration that the Earth experiences from the gravity of the Sun? If we plug in these numbers, then we get that it's 5.97 times 10 to the minus 3 meters per second squared. So how does this acceleration compare to little g? Well, it's much, much smaller than little g, isn't it? Little g is 9.8 meters per second squared. So it's a lot smaller, but the Sun is way bigger than the Earth. So why is the acceleration so much smaller than little g? We'll talk about it a little bit more in the next lecture, okay? For now, let's just note that it's much smaller, okay? But what about the force of gravity between the Earth and the Sun? What's the strength of the force? Well, we know the force of gravity, pointing this way, remember, straight toward the center, was that force of that caused the centripetal acceleration, right? It was the centripetal force in this problem. That's equal to MAC, and we have the mass of the Earth up here. So this force of gravity between the Sun and the Earth is 3.58 times 10 to the 22 newtons. And of course, the force of my weight, if we just say, for simplicity's sake, that I weigh 100 kilograms, is 980 newtons. So the force is much, much larger than between me and the Earth, right? As we would expect, because this force is large enough to give something as huge as the Earth a noticeable acceleration. We can clearly see that the Earth's velocity is changed by this force, right? It travels in a circle instead of flying straight. So that's our first clue as to why AC is so small compared to the force between me and the Earth near the Earth's surface, is because the Earth's mass is much, much larger, right? So the acceleration is going to be smaller because even for this huge force, the Earth's great big mass is going to give it a small acceleration. So that's our first clue. And then as for the other reasons that it turns out to be the value that it is, we'll cover that a little bit more in the next lecture, okay? In our next lecture, we're actually going to talk about Isaac Newton's universal law of gravitation, okay? And that'll give us a way of calculating the gravitational force directly. So let's look at this next example. Think of using a sling. You are spinning a rock around overhead in an approximately horizontal circle. Then you let go of one end of the sling and it stops redirecting the rock in a circle. If you are instantaneously ending the force applied to the rock, where should you let go in order to throw the rock in front of you? If the sling is about a meter long while holding a rock, and you spin it at 100 RPM, what speed will the rock leave the sling at? So if we think about a sling, it's got a rock that we're traveling in a circle here, and it has this radius that's the length of the sling, which we said is 1 meter. So R equals 1 meter. Okay? Now the first question, where should we let go in order to throw the rock in front of us? If we're spinning around in this direction, okay, clockwise, we should let the rock go right here because it has a velocity tangential to the circle, so that will fly right in front of us, okay? Now, a lot of people would kind of naively say you should let go here and then the rock will fly straight out. But remember, that was a product of thinking about these fictitious forces. That's what we talked about last time. If I let it go here, the rock won't actually go out this way. There is no force pulling it out this way, okay? If I let it go here, the rock will actually fly this way. Okay, so we let it go here, and it flies in front of us. Or you can imagine, depending on how far away something is, you want the arrow to point right at it. So if this is my target out here, then I might want to let go maybe here? No, that misses, huh? Maybe here. So that this tangential velocity points right at the target, right? But somewhere around in this area over here is going to throw it generally somewhere in front of us, right? So we let it go over here. It goes off with some velocity v, and then the question is, what is v? So if we're spinning it at 100 RPM, that's 100 revolutions per minute. And then, of course, there's 60 seconds in a minute, right? But you can see if I flip this fraction over, I would have 60 seconds per 100 revolutions. But remember when we talked about the period, we said the period was 1 revolution. So T equals the time, the seconds, for 1 revolution. All right? And that's going to equal 60 seconds per 100 revolutions. Okay? So T equals 60 over 100 seconds. When I multiply this, I'll get the RPM. Okay? So this is the time for 1 revolution. And then if I take 100 times this time, I'll have 60 seconds, right? And that'll give me the number of revolutions per 60 seconds or per minute. Okay. So this is our V. And we know that T equals 2 pi r over V. And so then V equals 2 pi r over t. And then units, again, really simple, right? We have meter on the top, we have seconds on the bottom, that's a velocity. Sanity, if we have a longer arm, if we have a longer sling here, then v goes up as r goes up. Okay? So if I want to travel in a bigger circle in the same amount of time, so if my period doesn't change and I travel in a bigger circle, I have to go faster, right? Because I have to go farther in the same amount of time. And v goes up as t goes down, right? Because it's on the bottom of the fraction. And again, if I travel the same size circle and it takes less time, then I have to go faster, right? So that makes sense. So both of those make sense. So then if we plug in the numbers, we find that t equals 10.5 meters per second. So now let's look at our last example for the day. Consider two blocks hanging on either side of a pulley. Block 1 on the left is a 15 kilogram block of steel. Block 2 on the right is an 18 kilogram block of steel. If they are both 1.6 meters off the ground to start, assuming that one block can rise high enough that the other block can hit the ground, which block hits the ground and how fast is it going when it hits the ground? So we have a pulley here, and we have two blocks hanging from it, M1 and M2. And M1 is 15 kilograms, and M2 is 18 kilograms. Okay? And then there's some distance, XF, off the ground. Okay? And XF equals 1.6 meters. Okay, so assuming that there's enough space for them to rise high enough to hit the ground, so not like the picture that I drew, which block hits the ground? So first off, this one is really easy to figure out which way they go, right? They're just hanging on a pulley, they each pull on each other, so they're going to go in the direction of the heavier block, mass 2. So they're going to go this way. Which block hits the ground? M2 hits the ground. And then how fast is it going when it hits the ground? So VF2 equals what? So let's start by finding the acceleration here. We have the force of gravity pulling down on this, Fg2. Force of gravity pulling down on this, Fg1. We have tension going up here, and we have tension going up here. We know for this problem that we're going to use Newton's second law, so the sum of the forces is equal to ma. And we know that we're going to use 1D kinematics. And we'll go ahead and use this one. Okay, that was an equation that I gave you guys. So let's start with block 1 and use Newton's second law. And I'm going to set my coordinate system like this, okay? Down is positive x hat, because ultimately I'm going to care about the speed of block 2 when it hits the ground, and I just want to make the velocity positive, okay? So, block 1, we have m1g, the weight of block 1 pointing down, right here, minus tension pulling back up. That's equal to minus m1a. Now, they're connected by a string. They're going to have the same acceleration, but block 1 is going to go up, right? And block 2 is going to go down. Up is negative in my coordinate system, so I end up with this. For block 2, I have m2g pointing down tension pointing up, and that equals M2A. This equation says that tension is equal to M1G plus M1A. And this equation says that tension is equal to M2G minus M2A. But now, Newton's third law tells me that this force, this tension, is an interaction. It's an interaction between block 1 and block 2. And of course, interactions have two sides, but just one magnitude, so these t's are the same. So what I get is M1G plus M1A equals M2G minus M2A. Okay, then I want to solve for A, so I'm going to have M2A plus M1A equals M2G minus M1G. Okay? So then finally this tells me that A equals M2... Oh, sorry, let's pull our G out. G times M2 minus M1 over M2 plus M1. Okay? So that's our A. And I'm going to put a square around it because I want to come back to it. Okay? But the question actually asks us about V. So let's find VF2 first. So VF2 is going to equal, if we just look at this equation and just plug in what we know, it's going to be the root of 2a xf, right? We can pick our coordinate system to make this 0, and they started from rest, so this is 0. And then if we plug in for a, we would get 2gxf times this little fraction of masses that we have here. Right? And that's all in a root. So that's our answer. The units are meters per second squared times meters, so meters squared per second squared. The kilograms in the top and bottom here cancel, so we end up with meters per second. So the units work. The sanity, you can, oh geez, I wrote A here. This was G, right, from here. This whole thing was A, so this is G. Didn't change anything for the units. We can see here that if the acceleration from gravity is bigger, we have a bigger velocity when we hit the ground. That makes sense. And we can see if we're higher up and we have more time to accumulate acceleration from falling a bigger distance, we're going faster when we hit the ground. That makes sense. Okay? And then the masses, let's skip those for now. I want to talk about the acceleration instead of the velocity here. So the acceleration in a problem like this, first off, we can see that, again, kilograms cancel in the fraction here, and G is meters per second squared, so our A is meters per second squared. That works. For sanity, we can see that A is always going to be less than G, because we have a difference of the two masses up top and a sum of the two masses down below. So this number is always going to be less than 1, right? And that's going to make this always smaller than G. And that makes sense, because if we have block 2, it has to accelerate slower than free fall because we have some tension pulling on it upward. Okay, so it always has to be smaller than G, and it is. And remember that when we did the frictionless ramp, this is actually the special case of our frictionless ramp where the angle of the ramp is 90 degrees, right? So that's interesting. This is what comes out, is these hanging blocks. And that's what we would expect if we made the quote-unquote ramp on the other one 90 degrees. It would just be a wall. And if it slides along a frictionless wall, it's actually like just hanging there, right? The other thing that we notice is that A gets bigger as M2 gets bigger, okay? So as we make M2 heavier, if we keep M1 the same, we get a bigger acceleration. And that makes sense, right? If we make the difference between masses of the two blocks bigger, we get a bigger acceleration. That's good, but always still less than g. And then the same thing, a gets bigger as m1 gets smaller. Okay, you can see that in this fraction. And that also makes sense, right? Again, as we make the difference between the two blocks bigger, we get something that's closer and closer to g, okay? You can also see that our a would change signs if m1 was bigger than m2, and that makes sense. That's telling us if m1 was bigger than m2, it would go this other direction, right? So there's a lot of interesting stuff in the algebraic form of this acceleration, okay? And I want you to keep this example in mind in the future. Eventually, when we start to consider energy, I'm going to revisit this one, and I'll use it to make a point about using conservation of energy to solve problems. But for now, just recognize that what we had to do with this one was use Newton's second law to find an acceleration, put the acceleration into 1D kinematics, and then solve and find a velocity, okay?